Question 4.1. The catapult is designed so that the weight of the beam and the weight of the empty wooden box have no effect on the tension in the rope, and suggest how the pivot position achieves this. Well, the center of mass of the beam and the box is at the same pivot, so sum of moment is 0 at this position. Anticlockwise moment, which is the weight of the beam, anticlockwise moment for the weight of the beam will be equal to clockwise moment for the weight of the box. Therefore, no resultant moment. Question 4.2. The stone in the counterweight have a total mass of 610 kilogram and the projectile weigh 250 newtons. So here's the projectile, that's 250 newtons, and the stone here, that's 210, and this is the tension rope here. There's a tension on that rope going in that direction, which means when you to resolve that vertically, so it's going to go, you're going to go from there to there. So we need that vertical resolution because it's asking us to calculate the tension in the rope. So we have to resolve this. We got the weight acting down, that's 250 newtons, that's the weight, we've been given that. And we need to work out the resolving force of that one. So this will be T sine 50 because we're using SOHCAHTOA, so sine of 50 will be opposite here, so that opposite here, opposite over hypotenuse. So let's call the opposite y, so that's the opposite there, y. So that'll be opposite y over hypotenuse, which is T. So to find y, we say y is T sine 50. And you can see that's what we've got here. Y is different. This is y here, that length is y. So the same direction as the vertical downward force. So the total vertical downward force here is going to be 250 newtons plus T sine 50. And times that distance if you take moment about that point. So that is what we call anti-clockwise moment, and this will be clockwise moment. So that total anti-clockwise moment, applying the principle of moment. So with the principle of moment, we say sum of the clockwise moment, sum of the clockwise moment will be equal to sum of the anti-clockwise moment. So the moment we've got here, the anti-clockwise moment is that, and the clockwise moment is that one here. So that would be 610 times 9.81, because that's the gravity and gravitational field strength times the mass here, and then times 1.5. So that would be the clockwise moment there, and anti-clockwise moment going in that direction. And from there, so 4 is a common factor because you're multiplying them by 4. So divide both sides by 4. When you multiply this one out, you get that. You divide both sides by 4, and now 4 goes. And you take the 250 to the other side, all right? So that's what, then you're left with T sine 50, and then you divide both sides by sine 50, and then we get T to be 2,600 newtons. Question 4.3. We've got a projectile and released from a height of 7.5 meters. So we've got the vertical, and then we're looking at the horizontal. From the diagram, we know you've got the height here, and we've got the range, and that's the range there. And that is starting initial, so we need to write down the SUVERT for the vertical. That's the SUVERT here for the vertical S, for the vertical distance, which is 7.5. So that's 7.5 here. And we need to then write U initial velocity, because it's starting from, we're talking about vertical now, so U is going to be 0. So that's U equal to 0. And the final velocity we don't know yet. A equals acceleration due to gravity here, because gravity is acting downward. And the time it takes for the vertical is the same time it takes for the horizontal. So time is common to both horizontal or vertical. In order to solve for the time, because that's what we can solve for here, we apply the SUVERT equation here, and we know U is 0, U times T, that will be 0. S So we've got 2s equals to gt squared, and t squared is 2s over g, square root both sides, t equals plus or minus root 2s over g, where t equals positive time, it's 2s over g. Substitute s is 7.5, 7.5 times 2 is 15, divided by 9.81. The time we get is 1.23 seconds. The speed to travel along the horizontal distance we're given that's 18. So speed is 18, making distance the subject. So distance is speed times time. We just calculate the time. So that'll be 18 times 1.23, and distance is 22 meters. So the range is 22 meters. Question 4.4. In another release, the sling is adjusted so that a projectile of the same mass is released just before the wooden beam is vertical. The projectile is not released horizontally. Discuss the effect this change has on the range of the catapult. Well, range will be greater, or range could be smaller. One component for the greater range, we were talking about the component of velocity upward. We have to resolve the component of velocity upward because we are saying that we've got a projectile, which is to say we have to do a resolution of component velocity upward there. So the rock will spend longer in the air and greater time for t, because it will take longer to get to the distance, and the range will be greater. The range will be smaller, one, if the counterweight will fall less far before projectile released, less energy transferred to rock. Initial speed of rock is less stroke horizontal. Velocity is reduced then. Small range or range is unchanged.